Hello everyone, I'm a former group member. So today I will share some of my progress in the new version of MuPro library, which we now call FaceField SDK, and also I will share some of my experience doing software development in the context of our group code development. Okay. So for a content list, in the first part, I will share a walkthrough of the FaceView SDK, which I will just compare with what's in our old library design and what's in our new library design, and then we will have a closer look at how the new library looks and how we can use it. And then in the second part after that, I will share my experience about software development. Yeah, so first I would like to maybe go back and have a brief history review of the FaceView code in our group. I think the very first FaceView code in our group probably is Dr. Chen's library, which I guess he developed even before 2000. And then Dr. Yulan Li has her own. Oh yeah, so a disclaimer. So here I only mainly talk about like code for ferroelectric, these part, not those metal or grain growth part. Yeah, and then around 2002, Dr.
Ferroelectric actually is before 2002. Actually, more like only the thin film. The 202 is for the thin film phase
Okay.
field code. We have our code in like 1997.
Oh, okay. Yeah, that's good to know. Yeah, so Dr. Yuan Li later, at least she has this thin film code that that I've seen it's just a single Fortran 77 file, and it's several thousands of lines and it's in serial. So yeah. And then I guess around 2011, Dr. Ben Winchester has his version of our ferroelectric program that is easier to read compared to Dr. Li's code. So Ben's code has like multiple files in Fortran 90, and also he add some new subroutines like the MSOF, which we still follow his naming convention today, and but his code is still in serial. And then roughly around 2013, Dr. Jason Brisson, he converted Ben's code into this library and main program structure. And also he added parallel using MPI into the code. Yeah. So I usually just consider Jason's code as the initial version of our MuPro library because this is the first version that has this library and main program structure. And after Jason, many of our group members contribute to the library. And around 2016, we just keep improving the library, and so that we can have multiple main programs, can share common subroutines in the library. And then afterwards, we improve some user friendliness of the library by adding like free format input and update the documentation. And around 2019, we have like first release of a commercial version of the MuPro library. But at that time, we don't. We're just distributing the binaries. We're not allowing the users to change any of the code. And the latest update is recently. So we are releasing this FaceView SDK, which we will allow the users to change the main program and just customize the program for their own needs. And so in this new release, I'm updating to Fortran 2008, and also I ditch FFCW and switch to the Fourier transform in Intel MKL. And even though I didn't change any of the core logic or algorithm part of the library, but I do almost completely change the structure of the library code and give it a more modular design. Yeah. So yeah, that's for the history. Before I dive into detail, I would like to talk about the name, what is SDK, and our goal with this SDK. So SDK simply means software development kit. And yeah, its name is already indicating our aim is to provide a set of tools to help users develop their own phase field softwares. So yeah, this collection of tools is what we call development kit. And so these tools at least should include like a core library that provides the subroutines, the types, the modules that the users can use. And it also should include a set of main program starter projects that user can then extend and customize for their own needs. So it also should include some tools for post-processing, for like structure generation, for data backup, and etc. Yeah, so that's the name and goal. And next, I would like to make a quick comparison between our just Jason's design of the library and our new library design, because I guess many of you have used and probably read Jason's Jason's version of the library. And so in Jason's version of the library, his idea is actually pretty simple. So he just wants to take a collection of subroutines from the main program and move them into a library. And yeah, that's all he wants to achieve. And when doing so, he met a problem, and that is some of the data, many of the data are both defined in the main program and also defined in the library. So for example, those nx, ny, and z, the system dimensions, right, and the strain stress, all of these are both defined in the main program and also in the library. So when you do when you compile the code, it will complain that you have like name conflicts. So to resolve this problem, Jason include this hidden data modules within the library that is only visible to the library, not visible to the main program. And so with this, any of the subroutines or anything in the main program is just using data defined in main program, and any subroutines within the library are just using data within this hidden data modules in the library, and they're not using data from the main program. So this solved the data isolation problem, but then the problem becomes how you can connect the data from the main program to the data hidden in the library. And so yeah, the solution is also just straightforward. For all of the data connection, Jason has this setup subroutines that you pass the data in main program as arguments of subroutines of this setup subroutines, and within the subroutine, he connect the argument data to the data in the library. Yeah, and then because he passed all of the parameters as arguments, Fortran needs us to tell it how these subroutines arguments are defined. And so Jason defined a interface between the main program and library that tells the main program how all of these library subroutines are defined. Okay, so that's just Jason's design. And this design is pretty simple and straightforward. It serves our needs pretty well for several years, yeah. But it has several problems. And the first one is it has a very long func module. So by func module, it's just this interface that I mentioned, which tells main program what are the arguments you need to pass, right? And here is an example of this func module file. This is not the latest, even an older version of MuPro, and you can see it easily exceed like 1,500 lines. And all of it defined is just some interface to the subroutines in the library. And if we keep adding more subroutines into our library, and this file will just simply keep growing longer and longer. And then another problem is relatively poor code reusability. So because all of the data is directly defined in these modules, in these hidden data modules. So let's take the ferroelectric model as an example. In ferroelectric model, we can have both polarization and oxygen octaedral tilt for the autoparameters. So these two autoparameters are actually very similar, but because they have two sets of data defined, and to interact with these data, though this is not the only way, but it's probably the most natural way is simply to define two sets of subroutines for each set of autoparameters. And you can see these two subroutines are exactly the same except for some differences in the parameters that it's using. Okay, so, and this is not actually not a very good coding practice. So, and then another problem is backward compatibility. So because all of the arguments are passed through the subroutine, all of the parameters are passed through this subroutine arguments. If we add some new functions into the subroutines, we just and we have more parameters that we need to pass. We just keep expanding these optional arguments, and so and also we just keep adding like layers and layers of wrapper functions above this actual subroutine. So this is not a very good practice, especially considering developers for our library is pretty limited. Yeah, and yeah, the last thing that I'm not happy with this design is simply it's not easy to develop because every subroutines are just under this huge library, and they share the same a bunch of data modules between these subroutines. So whenever you want to add a new subroutine, you need to have a relatively good understanding of other subroutines and also the relevant data module that you call before you can actually add a new subroutine. Okay, so with these problems in mind, I kind of propose a newer design for our library. So this is the look of our new library, and you can see instead of having individual subroutines, I group different functions into their own modules. Okay, so now the library contains many smaller modules, and each module is just responsible for one type of jobs. Okay, and these modules are as isolated from each other as possible. And so because they're isolated, and also the code base will become much smaller than the individual library. So it's easier to develop and maintain. And then you can see within each module, I have this derived type in Fortran. So with this derived type, I attach all of the data that this module needs. Right. So for example, in this TDGL module, I just put all of the data that you need to solve a TDGL equation into this type. And in this way, the data is no longer directly defined in a module. It is defined under a type. And because it is not directly defined in memory when you compile the library. So, and these data is only become available when the users define a type object in their main program. So there's and also there's no hidden data in the module. So there's no need to have this connection between the main program's data to the library's data. So now all of the data is just defined by the users. Okay, and then within this type that we defined, we also have several subroutines that is attached to this type. And so these types are just some operations you can have upon the data within this type. And this in this way, we solve the reusability problem, at least for the TDGL equation, because, for example, now instead of copy paste the same set of subroutines, you just need to define two type for this TDGL context type. So one for polarization and one for oxygen tilt. And then for each of the type, you can call their subroutines under that type, and that will give you the correct solver for that you need for the auto parameters. And then with this design, it also is much easier to keep backward compatible, because now all of the data that being used by these subroutines are just data within this type. So as long as we have a default value for these data in the types, any old main program should just work fine with newer library design. Yeah. Okay, so that's a rough structure of the new design, and let's just take a closer look. So yeah, so this is the look of our current folder structure in the library, and you can see I grouped all those functions, different functionalities, into their own modules, and each module has its own folder. And I also label these modules with a level number, and this level, so any of these modules can only use other modules that has the same and or smaller level number. So this is just one way to keep the dependency easier to track in the library. So yeah, so more basic functions will have smaller level number, and more integrated functionalities will have like higher module number. So let's take a look into one of the modules. So let's just use TDGL one as an example. And within this module, you can see the folder structure is like this. And actually for all of the modules, they have a similar folder structure. So you have a file that this is for a build system file, and you can ignore it for now. And then we have this interface file, which defines like what subroutines, what types are exposed to external users. And then you have some core logic files that just solve the actual equations or give some setups for the equations. And then we also recommend to define some testing functions to test subroutines within this file. Okay. Yeah, and then to just look more into the what is defined in the files. So for this interface file, and you can see we have an interface for the main program users. So that's this one. And then also we have an interface for other library modules that is this one. So for this TDGL module, these two are actually the same. They just expose the same type. But for some other library modules, it is very likely that we want some subroutines only exposed to the library developers, not to the MuPro users. So I think with this design, we have a much more flexibility in terms of what being exposed to others. And then the main part is just take a look at the core logic file, which now is just a single module for this one is for TDGL, right? And then within this module, we define a type. So this type contains all of the data that is necessary to solve the TDGL equation. And you can see there are also two subroutines attached to this type that first set up the solver and then solve the equation. Okay, and so also you see there's no other hidden data within the module, so there's no need to connect the data from the main library to the from the main program to the library. And if later you take a look at these setup subroutines, you will see, yeah, there's no connection from the main program, and all we need to do here is just some data preparation work to make the solver faster. Yeah. And then in the solver part, you see you don't need to have you don't need to copy paste this solver for different order parameters. You can have just one for all of them. Okay. Yeah. So this is the look of the and just yeah how we use it. When using it is very simple. So in general uh, the how say the main program design, you just follow the general design. You take some input from file, or you directly define in the main program, and then you do some setup, and that is doing here, right? And then after some calculation, you will solve the equation. And you can see as using the ferroelectric one as an example, if we have two order parameters, we just define two type for each. We just define one type for each of the order parameters, and that is the polarization, context, and the oxygen tilt. And then for the setup of those TDGL equations, you just simply pass the necessary parameters. You simply set the necessary parameters in these contexts. And then after a bunch of calculations, like solving other elastic equation, the Poisson equation, and get the all kinds of driving forces for these TDGL equation, before you solve it, you just tell this polarization context what is the right hand side that is the driving force for the equation, right? And you tell it what is the order parameter that we want to evolve in this in the solver, and then you call solve. So I think this design doesn't add much complexity compares to Jason's old design of just calling a subroutine, and you need to remember how you should put all of the parameters correctly. And but this new design gives you solves Jason's problem of like the code reusability and backward compatibility. Yeah, so this is actually I think knowing this is actually enough for you to get started with using the library. And the last thing is just you need to see what functions are available in the library. And so you can go to the GitHub page. Yeah, so you group members can just go to our GitHub page, and you can take a look at the source code, and that's one way you can see what is defined in it. But you can also go to our documentation site, and yeah, of course this is not complete, but we at least have many basic modules I have documented, and you can take a look and see what are the available types, and yeah, what subroutines you can call to use these types. And yeah, and then also, so that's for the library. And then for we also already have a simple example of the ferroelectric using our new library, and you can also go to this GitHub page and just take a look at these the source code that is calling from the library. Okay, yeah, and also for this ferroelectric main program, we also have a documentation site, but this one is even further from finished yet. Yeah, but I will complete it in the near future. Okay, yeah, and so that's actually all I have for the library part. And yeah, and then for a quick share of some of my experience in code development. Yeah, me personally, I met some pain points in doing software development, and like usually it's like I have too many versions of my code, and the build speed is slow, and if I change computer, the building will just fail. And also like debugging is difficult because I used to just use print to debug, right? And so also I used to code on the server directly using Vim, and that has unstable remote connection, and you will feel the lag whenever you type from time to time. Okay, and so yeah, to solve these pain points, I have changed my like workflow of development quite a bit in in along those years of doing code development. And so yeah, I switched to better version control system, better build system, and I'm I'm now using like better code editor. Yeah, so proper tools are important. And so for version control system, I'll just be quick. And there's choices out there, but you simply choose Git. And then for Git, there are also choices of Git services, but I will mostly recommend using GitHub. And then if you are using a version control system, you will no longer has those versioning issues, and it will tell you who make the changes, when the changes were made, and what changes are made. And then it also allows like collaborations between programmers, allows backup of your code, allows like branching and merging, all of these good stuff. So yeah, I consider Git as a must-use tool. So if you are not using it, I think you have to use it. And even if you feel it's not convenient or you really don't understand, but you just have to force yourself using it. Yeah, and so for some tips of using Git, I wouldn't go through it here, but you need to go and just take a look and try Git first, and then maybe you can come back and take a look of my tips. And yeah, the simple thing is just use more. You have to use Git for every changes you make to your code, and then you will get familiar and you will love it. Yeah. Yeah, and then
Well, you
for
can put the document presentation also link to be available also to the.
yeah, so this documentation is just available online. It's actually also a Git repository, and you can take a look at.
Oh, okay.
Yeah,
Okay.
yeah, I will send this link in the group email list. Okay, and then so that's
Okay.
for
What
the
about if we? Oh, yeah. Go ahead.
Yeah, okay. So that's for the versioning control. And then for build system, because I have the pain point of like build speed is slow, and because sometimes building the library from scratch can take several minutes. And also when you change from like our ACI server to Exceed, and the makefile simply doesn't work, and you need to change some of the pass to the libraries. And so yeah, so I'm now using a much more modern and automated build system, which is CMake. Of course, there are other choices out there, but I think CMake is the most popular one in the at least C++ code industry. And so benefit of CMake, it gives you like automation. It can automatically find, for example, the Intel libraries, the MPIs, so you don't need to configure the path yourself. And it's also cross-platform. So no, even if you are working on Windows, it can generate like for a Visual Studio project for you. And if you're on Mac, you can generate like Xcode project. Yeah, and this can also give you a faster building speed, because back in the back in the generator layer, it can call Ninja instead of Make, which is like maybe several times faster than Make. Yeah, so for CMake, this is not compulsory compared to Git. You can still use your Makefile, that's fine, but I think I highly recommend trying CMake. And It could be difficult to learn in the beginning, but in the long run, it's definitely save you a lot of time doing the building and testing of your code. Yeah, and also for some quick tips of using CMake. Yeah, also I wouldn't go through because you need to first try CMake and then you can understand some of the words in my tips. And the only one thing that I would like everyone to remember is when you try to give CMake a test, don't just search CMake in Google. You need to search modern CMake in Google and then start from there because yeah, the older version of CMake is very messy and you will quickly get lost. Okay. Okay, and then the last one is for code editor. So yeah, as I said, I also used to just code directly on the server using Vim, but after many years, I found Visual Studio, which is almost exactly what I need, and this is also I guess probably the most popular code editor for any kinds of uh, developer. Yeah. So
So I
it
can
has
just use it to log in from, what about if I have just a Mac laptop or PC
yeah,
laptop
I will
to,
quickly show how my workflow of
okay.
using Visual Studio Code. Yeah, yeah. So benefits, there's a lot of benefits. Like you can do remote connection. It automatically sync all of your settings across different machines. It has a huge amount of plugins. It has a nice interface for debugging. Blah blah blah. Yeah. So yeah, I think if you haven't tried, you definitely should try it. And yeah, at least it's much better than Vim and maybe Notepad++. Yeah. And
Maybe
so
your
for
users guide even include this also, you know,
yeah, okay. Oh, sure,
because
yeah, yeah.
I'm going to use your instruction. I'm going to install and one from my Mac laptop. If I'm able to do it, then which means you have a very good users guide.
Okay. Yeah,
Because
okay.
I'm not
I'll have
coding
that
for
aim in
everybody.
mind and I'll try to make it as clear as possible so that you can follow it and just have the program running from your laptop on our ACI server. Yeah.
Yeah, that would be great
Yeah.
because I want to get back to do some simulations myself.
Okay, cool.
I
Yeah.
really miss the coding part myself.
So here are some tips for using VS Code. So basically you should use the full power of this editor, just set up the remote connection, install proper plugins, and install some formatter to make your code like pleasant to read, and also use debugger instead of like me using print in the early days. Okay, so just for a quick walkthrough of how I use it. So like for example, let me open a new window here. Right, so you see, usually when I open a new window, it's like this. And because I usually do my programming on remote server and there is a plugin for remote connection. And if you use this plugin, it will list all of your, so all of the folders that you have previously visited, right? It will remember them. And you can see we have this FaceFieldSDK one on my server and we just open it. And if everything is configured correctly, you don't need to enter any password, username, or you don't need to cd into the directory you're working on. Yeah, it will just automatically enters there and it will have all of the files open as you just close it. And yeah, so everything will be just familiar to you and you can get to work directly. And so here because all of our code is using the Intel's compiler, so we need to set up the Intel's environment in this VS Code. So yeah, there is also plugin for that. You see, you just click and it's that's that's already set up. And then to build the system, there's also like plugin for that, and you can just click run a certain build task, and we already have a build all task for this kind of work. So you just click and then you see there's some console output, and this says it's like building. Yeah, of course it says no work done because I have built the same code previously, so there's no more building needed. But yeah, and then to start debugging, there's also this debugging plugin, and you don't need to, yeah, as I said, you don't need to print, and you should just use this debugger, and yeah, and just click start. It will start the program what you just compiled, and yeah, you see it get started, and yeah, you see it reached this breakpoint. So for when you use debugger, you need to define like breakpoints in your programs, and it will just stop at one of at the first breakpoint it met, and yeah, all of the breakpoints are listed here. And when it reach a breakpoint, you don't need to do the printing like this anymore, right? You can just enter the variables in here. It will give you the value, and you can even enter the value for these arrays, and it will give you values in the array. And yeah, you can even select specific variable in the array and see what's its value. So yeah, so that's the debugger. And yeah, so that's and after see for example, I've made some changes here, and you can save, and yeah, and then with those changes, there is this source control plugin that is basically using Git, and it is configured with GitHub. So you can just enter some comment for what changes you have just made, and then you commit the Git commit, and then it will be available on GitHub. So yeah, so this is a very quick walkthrough of like my usual workflow. Yeah, so I just highly recommend using it, and especially if you need to use the debugger. Yeah, that will save you a lot of time. Okay, yeah, that's all for my talk.
Okay, I've actually one more quick question. What about if I want to combine a routine written in C and another with our routines written in Fortran? Is that possible?
Yeah, sure, it's possible. So as you can see, not only in C, but also like in C++, it's possible. So you see, for example, here.
So basically, somebody can build a C module themselves and still using our code and combine with the other code.
Yeah. So
Fortran.
you see,
Okay.
in some of our module, we are already using like C or C++. Yeah, but even for C++,
Okay.
it's converted to C, but yeah, that's the same thing.
Okay, one last question. What about if, for example, we want to incorporate the codes like Ying and our mathematicians doing with the DOE, this Phoenix finite element code, the solvers want to combine. Would that need another code, or can be combined also the different solvers?
Finite element
solvers.
That's probably more difficult because here we have this base module which set up, and also the FFT one which set up the whole like solver space, right? But for
so it's better to have another version, another package, basically.
Yeah, probably it's easier to have another package. So everything in this package is probably should keep just like using FFT. That's okay.
But certainly the structure could be similar, right? Just using a set of solvers.
Yes, yeah. The structure is, we can have the same structure. Yeah.
Okay, these are all my questions.